Okay. This week, what we're going to be doing is we're going to be looking at a kind of small example of a code that corrects quantum errors. And this code won't be able to correct every quantum error in the world, but it'll be able to correct kind of enough quantum errors that would show some improvement in the performance of the quantum computer. And then we're going to see, why we're kind of stuck at just some set amount of improvement. And then we'll conclude with kind of looking forward. Next week, we'll talk about a much larger and more complicated stabilizer code that can correct kind of arbitrary quantum errors. And so this week is going to be our first example of working with stabilizer codes. And then everything we learned this week, we're going to apply next week to understand the surface code, which is, again, the kind of big goal of everyone, is implementing the surface code. Okay, so let's start with last time. So last time, I asked the following question for you to think about before this time. And this is a question that we're going to need to be able to answer if we want to understand kind of almost anything about quantum mechanics and quantum algorithms. And this is just a question about measurement. Let's say I have some state. What happens when I measure it? So in particular, let's say we have the state plus plus. And just as a reminder, when I say plus, I mean the state 1 over root 2, 0 plus 1. So if I have plus plus, this is the state where it's plus on the first qubit and plus on the second qubit. I can just kind of expand this out. This is 1/2 times 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. And this is just me, putting two pluses next to each other and multiplying it out, first, inner, outer, last. Okay, so the questions I asked was, first, what happens when we measure the x operator on the first qubit? Second, what happens when we measure the z operator on the first qubit? Third, what happens if I measure the operator z1, z2? And z1, z2, it's not like I measure the first qubit in z and then I measure the second qubit in z. It's that I measure z1, z2. And similarly, what happens if I measure x1, z2? And just as a general way to think about this is a reminder of like the fundamental measurement postulate in quantum mechanics, which is that when you measure a state, you change the state. And this is something that you should have heard over and over again. And how do you change it? You project into the state that has a definite value of the operator you're measuring. So for example, the plus state over here is 1 over the square root of 2, 0 plus 1. So if I measure the z operator, well, the z operator doesn't have a definite value in the plus state. The plus state is not an operator, or it's not a state with a definite value of z, but we can write it as a state that has z equals 1 plus a state that has z equals -1. And then when we measure z, we'll randomly get one of these options. Quantum mechanics is truly random. And if we get z equals 1, we go into the state with z equals 1. And if we get z equals -1, we go into the state with z equals -1. Does this make sense to everyone? Or is there questions about how I'm saying this? Okay.
So you said right now that quantum mechanics is truly random.
Yes.
So in that way, when we measure probabilities, then it's a little bit because if it is truly random, then means, for example, let's take the Hardeman gate. Then half of times it gets, white, and means 0, and half of times it gets 1. So in that way,
right. So you're saying that if we take, let me just make sure I understand what you're saying. You're saying that if I take a Hadamard gate on the state 0, and
Telling
then I
you, you can't really figure out the word, right? Why? You know why it's like that? The phone had screen issue. So in the process of trying to key in those stuff, you know, I actually didn't see. That's why one of the reasons why I want to change, because there's nothing is impossible. It can be changed. Sorry? Okay. Okay, I'll try and do it. I'll see what I can do. All right, you can leave it. All right.
Okay, so sorry. So you're saying that if we take the Hadamard gate on 0, then we measure Z, then we get a random outcome. Yes?
Yes, I mean that. But yeah. Okay. I get it. I now understand what was what
because if we put the Hadamard gate on 0, then we're kind of just in this state again, and then we have those two possibilities.
Yeah, I get it. Thank you.
Okay, so then let me just ask everyone here, what's the answer to the first part of this exercise? What happens if I measure x1, the x operator on the first qubit? And anyone can answer in either the chat or they can just unmute themselves, but somebody's got to answer.
After measurement, it could be either 0 or 1, and in 0 or 1 state. When we apply X gate on the first qubit.
So the first qubit is in the state plus. So what happens if I apply the X gate to the state plus?
It remains in the state plus, but after measurement, its wave function collapses.
But I'm measuring X.
If we measure it, we'll get expectation value as 0. Sorry, 1.
The expectation value will be 1. That's correct. Because remember, X acting on the plus state. So just as a note, X acting on the 0 state gives me 1. X acting on the 1 state gives me 0. This is kind of the definition of the X operator, which means that X acting on the plus state, this is 1 over the square root of 2, X acting on 0 plus X acting on 1. Which is the same as 1 over the square root of 2, 1 plus 0. Because X acting on 0 gives me 1, X acting on 1 gives me 0. So this is just, you get back the plus state. So the plus state is already a state with X equals 1. So we start off in a state with x1 equals to 1 and x2 equals to 1. So in this state, we have x1 equals 1, x2 equals 1. So when we measure x1, we're going to project into a state with a definite value of x1, but there's only one state that it has that, and we're already in it. So our state doesn't change. We'll definitely measure x1 equals 1, and our state will stay the same. So that's for the first question. What about if we measure Z1 on the first qubit?
It will become minus ket state, like 1 by root 2, ket 0 minus ket 1.
That's if you operate with Z1 on the first qubit. What happens if you measure Z1?
Its expectation value will be 0.
The expectation value will be 0. So half the time we'll get 1 and half the time we'll get minus 1.
Yeah.
And so the way I'm going to draw that is, okay, so let's think about this. So a plus state, we have right here that plus is, 1 over the root 2, 0 plus 1. So let's write that out. So I'm rewriting this first plus as 0 plus 1, and the second plus I'm just leaving as plus because who cares? We're not even measuring it. So that means that this state is a sum of a state with z equals 1, z1 equals 1, and Z1 equals -1. So there are two possible outcomes, right? This one has Z1 equals 1 because the first qubit is in a state with Z1 equals 1. And this one has Z1 equals -1 because the first qubit is in a state that Z1 acts as -1 on. So if I measure Z1, I either randomly get the first outcome, Z1 equals 1, in which case my state after is the state with Z1 equals 1, or I randomly get the second outcome, which is right here. Questions about this? Because I'm about to ask you about Z1 times Z2. Okay, here I am. I'm asking you about Z1 times Z2. What happens if you measure Z1 times Z2? And I've written out down here that plus times plus, you can write it out as 1/2 0 times 0 plus 0 times 1 plus 1 times 0 plus 1 times 1. So you might think to yourself, like, what is Z1 times Z2 on this state? What is it on this state? What is it on this state? And what is it on this state?
Z1 times Z2 should also be 0.
Okay, what is Z1 times Z2 on this first state?
1.
What about the second state?
-1.
Third?
-1.
And last one?
1.
Right, great. So Z1 times Z2 can only take on two values. It can take on a value of 1 or -1. And it takes each value half the time in this case. So we're going to see that half the time we measure +1. If we measure +1, then we just end up in the states with the value +1. This is the fundamental rule of quantum mechanics. You measure it and you project into the state with that value. So now we have 1/√2, 0, 0 plus 1, 1, because those are the only two states that have Z1, Z2 equals 1. And then if we measure -1, we end up in the states with the value -1. Questions about this? This isn't just important for error correction. This will be important for, anything in quantum computing. So if you're not understanding it, we can slow down and just talk about this for an hour. It doesn't matter. But ask questions if you have them.
Are you able to see the chat?
Yes. Yeah, people can ask questions in the chat if they're more comfortable that way. Although sometimes it helps to have some back and forth if you're confused. Okay, and I have one last question here, which is, what happens if we? Right, okay, so yeah, so a question in the chat. When you measure Z1, Z2, you're measuring the eigenvalues of that operator, Z1, Z2. So for example, 0, 0, one way to say it using like fancy math calculators, 0, 0 is an eigenstate of Z1, Z2 with eigenvalue 1, because the value of Z1 times the value of Z2 here is 1. And what I mean when I say it's an eigenstate is it's just a state with a definite value of Z1, Z2. So for example, plus is not an eigenstate of Z because it doesn't have a definite value of Z. On the other hand, 0 is an eigenstate of Z because it has a definite value of Z, and 1 is an eigenstate of Z because it has a definite value of Z. So this is an eigenstate because it has a value of 1 for Z1, Z2. This one has a value of -1. This one has a value of -1. This one has a value of 1. And when I say you're going to measure an operator, what I mean is you're going to measure its eigenvalue. Does that answer your question? Great. Okay. So yeah, last question is what happens if I measure x1, z2? And the whole game here is when I write an operator out, I should write that state in a form that makes it clear what happens when I measure that operator. So I want to write it out in a state so that the first qubit is an eigenstate of the X operator and the second qubit is an eigenstate of the Z operator. So I've written this out, for example, plus plus. The first qubit is already in an eigenstate of the X operator. And the second qubit is in the plus state. So I can write it as 0 plus 1. And so, yeah, so somebody's written in the chat that we're again going to have 0 expectation value. And that's right. So let me ask, what's the value of x1, z2 on this state? The product of x1 and z2. So this one, x takes the value 1 and z takes the value 1. So their product is 1. And what about here?
-1.
Right, exactly. So x takes the value 1 still, but z takes the value -1. So we're in -1. Okay. So then that tells us that we have two possibilities. We can measure 1, in which case we go into the state plus 0. Or we can measure -1, in which case we go into the state plus 1. Okay, that's multi-qubit measurement. And Peter's asking a question. So yeah, to find the probability, I'm taking, I'm taking the product of this state with the state I want to measure it in. So for example, the inner product of this with plus 0. And then I'm squaring it. Another way to say that, sorry, there should be a square root here. That's a typo. Another way to say that is, you know, if psi equals alpha times the first eigenstate times the second eigenstate, the probability of measuring this eigenstate is alpha squared, where I used an absolute value in case we have complex numbers running around. But and then the probability of measuring this one is beta squared. So here, each one of these has a factor 1/√2 in front of it. So I square that factor of 1/√2, and I get that each one of these happens with exactly probability 1/2, which is why people can say that the expectation value is 0, because half the time we measure 1 and half the time we measure -1. So yeah, if you want me to write this out in full, I'd say that, okay, we have our wave function 1/√2. Let me write this out. So we have our wave function 1/√2 plus 0 plus 1. And if I want to know the probability of measuring this state, what I do is I take the inner product with plus 0. And then I'm going to take this at absolute value squared. So that's the same thing as 1/√2 times plus 0, 0 plus 0, 1. Where I've just taken this and I've taken the inner product with this plus the inner product with this. So I've distributed it. And then the key thing to realize is that 0 inner product 1 is just equal to 0. So the second term is 0. And this term is equal to 1. So this just equals 1/2. Okay. So that's multi-qubit measurement. If anyone has more questions about this, this is a good time to ask them. Okay, let's continue then.
I have a
Oh.
question.
Please, yes. Go.
Yeah. So I noticed that in between these exercises, like you created the Bell states, phi plus and I think psi minus. So are they going to be relevant in error correction later on, or that just a coincidence for example purpose?
They're, like here, like by measuring Z1, Z2, we get a Bell state.
Yeah.
So right now, this is just a coincidence. This has like this is a useful fact that by measuring the Z1, Z2 operator, you can get Bell states. And we'll kind of see an example of this in a minute for a small error correcting code, but this turns out to not be a super useful fact for larger error correcting codes. But it's a useful fact like other places. It's just something to keep in mind that if you start with just a product state plus plus, which has no entanglement, right, the first qubit is totally independent of the second qubit. It is a useful fact to know that you can create entanglement just by measuring the operators Z1, Z2. And I'll just note this is just for your own edification and it's nothing to do with error correction, but there are quantum computing platforms where people have proposed that instead of using gates that entangle two qubits, like a C0 gate, in general, you know, a quantum computer needs some 2-qubit gate so that it's not just like doing things independently to qubits, that they can actually interact with each other. There are platforms that people have proposed where instead of doing that, you just do Z1, Z2 measurements to entangle qubits. That's just
Okay, thanks.
yeah. Okay, so now we're going to start on the kind of main topic for today, which is the stabilizer formalism. So remember that last week what we said was that the problem with just storing a quantum state a bunch of times and then hoping you could like check things to make sure errors were correct was that you have to be very careful what measurements you make on a quantum system. Because in classical systems, you can always just measure them and see was an error there or not. But in quantum mechanics, as we just looked at, every time you measure one of these states, you change the state. So one approach to writing down an error correcting code is to just write down a small list of observables that we're going to be allowed to measure. And those observables are called the stabilizers. And there's some small list of observables that if we don't have an error, they're supposed to be equal to 1. And because they're always supposed to be equal to 1, you can measure them without changing the state. And we'll see an example of this in a second. So here's our first example, and it's called the quantum repetition code. And so it has 2 stabilizers, and the stabilizers are Z1, Z2, and Z2, Z3. This is a code on 3 qubits. So there's 3 qubits running around, but we're going to say that if there's no error, we're going to want Z1, Z2 to be 1 and Z2, Z3 to be 1. So here's just exercise. Just name me some states that have Z1, Z2 equal to 1. Give me an example of a state that has Z1, Z2 equal to 1, and then give me an example of a state that has Z2, Z3 equal to 1.
All 3 to be 0, state 0.
Right. So if we have, for example, the state, actually, let me go forward. Yeah, actually, let me not go forward. Okay, so if we have all 3 0, 0, 0, that's a state where Z1 is 1, Z2 is 1, and Z3 is 1. So that means that Z1 times Z2 is 1, and Z2 times Z3 is 1. Somebody give me one more state. Oh, okay, somebody said it in chat. We can also have all 3 of these be -1 because -1 times -1 is 1. So we can have the state 1, 1, 1. And those are basically all the states, except they're not like exactly all the states, just because we're in quantum mechanics, so we can have superpositions of them. So just to write this out, so the state 0, 0, and then anything, and 1, 1, and anything have Z1, Z2 equal to 1. The state anything 0, 0, and anything 1, 1 have Z2, Z3 equal to 1. So putting that together, well, 0, 0, 0, and 1, 1, 1 are states in our state, are states where these stabilizers are equal to 1, which means that we can actually have arbitrary superpositions. So here's my proposition for a code. The proposition is, let's say we had some state. Okay, so in general, a state that has Z1, Z2 equal to 1 and Z2, Z3 equal to 1 is going to be a superposition of 0, 0, 0 and 1, 1, 1. Because even if you're in a superposition of these two states, you'll still have those two values of the stabilizer. Okay, so here's my proposition then. Let's say we want to store the state alpha times 0 plus beta times 1. This is an arbitrary single qubit state. Instead of storing that state, which is very vulnerable to errors, we're going to send it to the state alpha times 0, 0, 0 plus beta times 1, 1, 1. And the claim is that maybe this is going to help us protect the information. And so let's see how this helps us protect the quantum information. So don't think about this exercise too hard. What happens if we measure Z1 times Z2 of this state right here? And anyone is allowed to answer.
Alpha plus beta.
What do you mean alpha plus beta?
If we measure in Z1, Z2, then we get the scalar quantity alpha plus beta.
Careful, because this first state has Z1, Z2 equal to what?
1.
And the second one has Z1, Z2 equal to?
Sorry, if I understand correctly, Z1 is on the first qubit, right?
Yes. So
It's
this
again 1, right?
right. They both have Z1, Z2 equal to 1.
Yes.
So what that means is that if I'm already in a state with Z1, Z2 equal to 1, when I measure Z1, Z2, nothing happens to it. So here's kind of how to think about this. We start off in a state, and this whole state has Z1, Z2 equal to 1. So if I measure Z1, Z2, I'm going to project into the state with Z1, Z2 equal to 1, where I'm already at. So I'm definitely going to measure Z1, Z2 equal to 1, and nothing's going to happen to my state. Another way to say this, Harsh said it in chat, is that the expectation value of this is 1, because I'm always going to measure Z1, Z2 equal to 1. And so I don't collapse my wave function at all, because my wave function is already as collapsed as it can get when you measure Z1, Z2. So then let me ask a follow-up question, which is hopefully straightforward. What happens if we measure Z2, Z3?
Same.
Right. So there's no difference between Z2, Z3, and Z1, Z2. Both of them have expectation, or both of them have a definite value of 1 in our state. So nothing happens. And so what this is telling us is, okay, we have this encoded state. It's alpha 00 plus beta 111. But as long as we're only measuring Z1, Z2, and Z2, Z3, we don't collapse the state. We're free to just keep measuring them as often as we want, and we don't destroy our information. And so what we're going to see now is that this allows us to actually detect errors. So let's say one of our qubits experiences an error. Let's say X2 happens accidentally. We accidentally apply the X2 operator. So what does this do? This X2 operator, it just acts on the second qubit and flips it. Because, you know, as a reminder, which I put up in this corner, this is how X acts on 0 and 1. This is the definition of X. So if I accidentally have an X operator happen, my state becomes alpha times 010 plus beta times 101. I flipped the middle qubit. And so if I flip the middle qubit, now we can ask ourselves, what happens if we measure Z1 times Z2 on this state? Anyone can answer, or anyone can ask a question if they don't understand. And one thing you might want to ask yourself is, what is Z1 times Z2 for this piece? And what is Z1 times Z2 for this piece? Okay, great. I'm getting some answers in the chat. So if we look at Z1 times Z2 for the first piece, well, Z1 is 1 still here, and Z2 is -1. So this one has Z1 times Z2 as -1. And this one also, this one has a -1 times a 1. So this one has Z1, Z2 equals -1. So what that means is, if we measure Z1 times Z2, we still don't change our state. We're still in like a definite value of Z1, Z2. But we'll get back the answer -1. And we knew we were supposed to get back the answer 1. So we'll be like, that's interesting. We're just going along, we're measuring Z1, Z2, and we get 1, 1, 1, 1, -1. That tells us that something happened somewhere. And then, you know, the next thing to think about is what happens if we measure Z2 times Z3.
It will again have the eigenvalue -1.
Great, that's exactly right. Good, people in the chat are also there. Right, because we flip the middle qubit, which means that it like changes the value of these two guys, but it also changes the value of these two guys because, you know, it's the middle qubit, it changes both of them. And so then if we look at, you know, this times this, that's Z2 times Z3 equals -1, and similarly here. So we're there. We don't change the state. Both of these have Z2, Z3 to be -1, but we get a signal. We say, aha, Z2, Z3 equals -1. So if we want to figure out what error happened, we can make this, so the stabilizers tell us there must have been an error. And then if we want to figure out what error happened, we can kind of make this table of some different errors. So we've already said that if we have the X2 error happen, then the state after the error is going to be alpha 010 plus beta 101. And we're going to measure Z1, Z2 to be -1 and Z2, Z3 to be -1. We can keep going and just fill in this table for all possible errors, or all possible X errors for now. I'm just going to focus on X's. So if an X1 error happens, that flips the first qubit. So then if an X1 error happened, what is the value of Z1 times Z2? And what's the value of Z2 times Z3? Right, so the value of Z1 times Z2 is 1, or sorry, is -1, and then the value of Z2, Z3 is 1. right? These two disagree, so we get a -1, but these two still agree, so we get +1. And similarly, if we have an x3 error, we flip the last qubit, and flipping the last qubit doesn't affect the first two, Z1, Z2s, but it affects Z2, Z3. So this gives us a little table. It tells us that, listen, if both of my stabilizers measure -1, I should think an x2 error happened. If the first stabilizer measures -1, I should think x1 happened. And if the third stabilizer measures -1, I should think x3 happened. Now, we could also ask ourselves, what happens if two errors happen? Well, if x1 times x2 happens, that flips both of these qubits. And in that case, Z1 times Z2 is still 1, and Z2 times Z3 is -1. And we can do that for this other 2 qubit errors. If we flip the last 2 qubits, this first stabilizer is -1, the second is +1. And then similarly, if we flip the first and the last qubits, sorry, I don't know why my PowerPoint is frozen. Give me 1 second. Okay, we get -1, -1. And the thing to notice here is that, okay, we can tell these 3 errors, we can tell the first 3 errors apart. We can tell these 3 apart. We can tell the difference between an x1, an x2, and an x3 error, but we can't tell the difference between an x1, x2 error and an x3 error. And we can't tell the difference between, these errors are pointing wrong, this error and that error. And we can't tell the difference between this error and that error. Does that make sense? If an x1 error happened, we measure -1 +1. But if an x2, x3 error happened, we also measure -1 +1. So we don't know which of those errors happened. And that's why this is a code that only corrects small errors. So just to say it explicitly, these stabilizers let us detect a single X error. But if 2 X errors happen to happen at the same time, then we're just out of luck. So, you know, if the errors come just one at a time, we can keep detecting them and correcting them and detecting them and correcting them. If they ever arrive 2 at once or 3 at once, we don't have any hope of detecting them with this code. Questions about this? Okay, let's continue. So, oh wait. So does this mean the stabilizer code is not suitable for a large scale? That's absolutely correct. This means that this stabilizer code will help reduce the probability of errors because, you know, you can correct all the single qubit errors, and single qubit errors are the most common kind. But if you have 2 happen at once, then you're just done. So it's reducing the probability of errors, and that might be enough if your computation is short enough. But in general, all of the stabilizer codes we see today are going to be examples of small codes that can reduce the probabilities of errors, but not send them to 0. And then next week, we're going to see an example of a code where you can kind of reduce the probability of errors arbitrarily well. And then those are kind of the codes that we look at for a large scale computation. And we're about to see one more problem with this simple code, which means that it's even less suitable for the large scale. Let's say one of our qubits experiences a Z2 error. So if I act on this state with Z2, Z2 sends 0 to 0, so it doesn't do anything to these first things, and it sends 1 to -1. So we just get a minus sign here. And so here's an exercise. What happens if we measure Z1, Z2 of this new state that had an error on it?
The eigenvalue would be +1. The state would remain unchanged, I guess.
Yes. So we still have a +1 of Z1, Z2. Great. And what about Z2, Z3?
Yeah, same as before.
Yep. So Z1, Z2 still gives us 1, and Z2, Z3 still gives us 1. One way to say this, by the way, is that, and if you don't understand what I'm saying, don't worry about it. It's not important, but for people who like have read this vocabulary, I want to use it. One way to say this is that the error Z2 commutes with these operators. And if an operator commutes with another operator, applying it doesn't change the eigenvalue. So Z2 commutes with Z1, Z2, and it commutes with Z2, Z3. So when Z2 happens, it doesn't change the eigenvalue of Z1, Z2, or Z2, Z3. The punchline of all of this is that these stabilizers let us detect X errors, but they can't detect Z errors. So again, they're reducing the error rate in our code, but they're not doing anything about an erroneous Z error. They are doing something about an erroneous X error. If the X errors are the most common thing in your qubits, then maybe this is a good code to start with, but it's clearly not complete, because the fundamental rule of quantum error correction is that qubits can have more than one type of error. Like bits can essentially only have X errors, if you want to think about it that way. And X takes a 0 to a 1 and a 1 to a 0. But qubits can have these Z errors, which change signs, which doesn't happen in a classical computer. So if we want to correct all types of errors, we need to be able to correct X and Z errors. So let me see how I'm doing on time.
Yeah, I have a question.
Yes, please.
So given that I have a Z error, so that means I can't detect the error with Z1, Z2. Does it have to do with the commutation relation, that if I have the same operators, their commutation would be 0, then they can't be used as a stabilizer. Only if commutation is non-zero, then I can use them as a stabilizer. Is there something kind of like that?
Yeah, so I'm gonna kind of lay it out on the next slide, but the idea is Z1, Z2, it commutes with Z2, say. This equals 0, which means that Z1, Z2 cannot detect Z2 errors. Because if a Z2 error happens, it doesn't affect the value of Z1, Z2.
Yeah, because they have common eigenvalues.
Exactly, because we're already in an eigenstate of this guy. And so if I act with this, I stay in an eigenstate of this guy. But on the other hand, it's easy to check that Z1, Z2, the commutator of this, and say X2 is definitely not 0. Which is why when you act with this, it changes the value of this. Okay, so now I'm going to kind of lay out, I'm not going to prove these rules, but they're not terrible to prove if you want to think about it yourself, or talk to me about it later. You can probably figure out why each of these are the 3 rules. But there are 3 rules of stabilizers that you need to kind of follow when you're designing a stabilizer code to correct quantum errors. So the first rule is that a stabilizer with an X on a qubit detects Z errors on that qubit, but it doesn't detect X errors on that qubit. And similarly, a stabilizer with a Z on that qubit detects X errors on that qubit. And this kind of gets to what we were just talking about. If there's a stabilizer has an X on a certain qubit, then it doesn't commute with Z's on that qubit. And same with Z's and X's. So just as an example, say we have a stabilizer X1, Z2, X4. Okay, which I've kind of written out here. Okay, so what's a +1 eigenstate of this operator? Well, it's 1 + 1 eigenstate of this operator is like a plus on the first qubit, a 1 on the second qubit, anything on the third qubit, because who cares? And then a minus on the fourth qubit. So this is one, there are many examples of states with this thing having +1, but one is that the first one is 1, the second one is -1, and the fourth one is -1. So this is an example of one state. If I act with a Z1 on this state, remember that the Z operator takes the plus state to the minus state, as I've put in this little box up here. So the Z1 operator takes this plus to this minus state. And this state, let me write this out. Sorry. So this state has the stabilizer equal to +1, but this state has the stabilizer equal to -1 because it's minus times minus times minus. So a Z1 error sends the stabilizer to minus itself, and we can detect it. On the other hand, if there's, and similarly, an X2 error would send this 1 to 0, which would also send a +1 to a -1, and we can detect that. On the other hand, a Z2 error, so a Z error on this qubit, sends this state to the same state, but with a minus sign in front of it, which has the same value of X1, Z2, X4. So we can't detect this error. We can only detect Z errors here, and we can detect X errors here, but we can't detect X errors here or Z errors here. Okay, that's the first rule of stabilizers. Then, okay, we have a second rule of stabilizers. When we're writing down all the stabilizers we'd like to measure, we can't write down two incompatible stabilizers. Like there could be two stabilizers that they can't both be true at the same time. So two stabilizers are compatible if they disagree on an odd number of qubits. So let me give an example of what I mean by that. Let's say I wanted to have a stabilizer X1 and Z1. I was like, we'll have X1 and Z1 be stabilizers. We'll have X1 equal to 1 and Z1 equal to 1. If I say X1 should be 1, that means I'm saying my state should be plus. But if I say Z1 should be 1, that's saying that my state should be 0. It can't be both plus and 0 at the same time. So me saying that I want both X1 and Z1 to be a stabilizer is incoherent. I can't say that. On the other hand, if we think about the state X1, X2, and Z1, Z2, these disagree on an even number of qubits. They disagree on X1 and they disagree on qubit 1 and qubit 2. And it turns out that that means that we can enforce them both at the same time. You can check that the state 0, 0 plus 1, 1 is, well, clearly it's a +1 eigenstate of Z1 times Z2. But you can also check that you can rewrite it as minus minus plus plus plus, which means it's also an eigenstate of X1, X2. So the rule is these two stabilizers up here, they disagreed on a single qubit. They disagreed on an odd number of qubits, and they were incompatible. But these two stabilizers down here disagree on an even number of qubits, and they are compatible. So we always have to make them disagree on an odd number of qubits. They could disagree, or sorry, on an, this should be even. That's why I'm getting mixed up. Okay, they just have to disagree on an even number of qubits. So this one disagrees on an odd number of qubits, this one disagrees on an even number of qubits, and we want to be in this situation. Apologies for the typo. And finally, the third rule is that if we have two errors on our stabilizer, that's the same as no errors on our stabilizer. So for example, if we have the stabilizer X1 times X2, then this stabilizer can detect Z errors here or Z error here, because those are the errors that disagree with that qubit stabilizer. But if we have a Z1 times Z2 error happening, if we have both a Z1 and a Z2 error happening, that would take a state plus plus to minus minus. And this state has X1, X2 equals to 1, and this state also has X1, X2 equal to 1, which means that two errors look like they had no errors. So a Z1, Z2 error still keeps X1 times X2 equals to 1. Questions about these three rules?
I have a small question regarding the first rule.
Yes.
The third example where you put error as Z2.
Yeah.
So in that case also we get the value as 1 after putting the error Z2. So
Yes.
plus 1 minus goes to -1 and minus.
Sorry, say that again.
So the last case where we put the Z2 error.
Yeah.
So like the plus and 1.
This.
Yeah, this has
Oh, sorry. This should be a plus right here. That's correct. Yeah. This should be a plus.
yeah.
Yes. Right, because the Z2 error doesn't change this first qubit at all.
Yeah, so now even the output final state also has expectation value as 1, so we cannot detect it, right?
Exactly, exactly. So the point is we can detect Z errors on this qubit, we can detect X errors on this qubit, but we can't detect Z errors on this qubit.
Yeah, okay.
So this
Thanks.
is a detectable error, this is a detectable error, this is not a detectable error. With this stabilizer, we need a different stabilizer to help us find the Z2 errors. Other questions?
Can you explain the rule 2 again, please?
So rule 2 is 2 stabilizers are compatible if they disagree on an even number of qubits. So what I mean is that if I want to have a bunch of stabilizers in my code, I can't have 2 stabilizers that tell me to be in states that aren't even compatible with each other. So for example, if I wanted both X1 and Z1 to be a stabilizer, let's say I wanted to write down some code and I was like, X1 is going to be a stabilizer in this code and Z1 is going to be a stabilizer in this code. That's not possible because if I want X1 to be a stabilizer in the code, that means that the first qubit has to be in this state. That's what it means if X1 is a stabilizer, right? That means that my first qubit has to be in a state with X1 equals to 1.
Yes.
But if I want Z1 to be a stabilizer, that means that my first qubit has to be in the state 0.
Yes. Okay. Okay.
These 2 states aren't equal, so I have to pick one. I can either pick X1 to be a stabilizer or I can pick Z1 to be a stabilizer, but I can't pick both. And we're going to say that the reason this happens is because these 2 stabilizers disagree on an odd number of qubits. But stabilizers, they have different, right? They disagree, by which I mean, one, I want to have an X there, and the other, I want to have a Z there. And if you disagree on an odd number of qubits, you can't be true, both be true at the same time, it turns out. I haven't proven this, but I'm just stating it as a claim. And then my second claim is that if you disagree on an even number of qubits, like X1, X2, and Z1, Z2 disagree on an even number of qubits, there actually is a state that has both X1, X2, and Z1, Z2 as a stabilizer. And it's this state I've written down here. So these you actually can demand at the same time. You can say, I want X1, X2, and Z1, Z2 to be a stabilizer of my state. And you can actually find a state that that's true for.
Yes, yes, got it. Thank you.
Okay, yeah, so great. So somebody wrote in the chat, why are we only caring about X and Z? What about Y? And there's a more general question here, which is like, what if we had an erroneous Hadamard gate applied? What if we had an erroneous S gate applied? What if we, like, there's so many errors that could happen. Why are we only talking about X's and Z's? So this is an important theorem that I'm not going to prove right now just for want of time, but if you look up any of the kind of notes I posted in the Discord, if you wanted to look through those, what you can prove is that, and this is like really powerful, and I've been kind of implicitly using this the whole time, is that you definitely need to be able to correct X errors and Z errors if you want to get anywhere. But the powerful thing is that you can prove that if you can correct X and Z errors, you can actually correct every type of error. And in the case of the Y operator, the reason you can correct Y errors is because the Y operator is just I times X times Z. So a Y error just looks like an X error and a Z error happening at the same time. Which means that if our code can correct Z errors and it can correct X errors, then it can probably figure out that a Y error happened by just saying, oh, look, an X and a Z error happened on the same qubit. then there are other questions about like, what if an erroneous Hadamard operator got applied? What if an erroneous tiny rotation about the z-axis got applied? But you can do a little bit more work and prove that all of those can be corrected as long as you can correct X and Z errors. I'm happy to stick around afterwards and like talk through this if you're interested, but it's also in any standard, it's definitely in both of the notes that I posted on the Discord about error correction, and it's definitely in any standard reference about error correction that you would find. But that's why we're only going to focus on X and Z errors. We know we definitely have to be able to correct both of them. If we can't correct both of them, we're done. But it turns out that that's also sufficient. If we can correct both of them, we are done. Okay. So let's talk about our first example. And this is the only example we're going to talk about today because, we're running a little short on time and I don't want to hold you too long. But here's the first example of a code that can correct both X and Z errors. So here I've just put these like 3 rules in the sidebar. So just remember that the stabilizers with X's on them are going to flip when they get a Z error. The stabilizers with Z's on them are going to flip when they get hit with an X error. And you can check for yourself that all of these stabilizers disagree on an even number of qubits. So for example, this first stabilizer and this third stabilizer disagree on the first 2 qubits. It's an even number. And this is the very first quantum error correcting code that was ever written down. It was written down by Peter Shor because people kept hassling him about how his algorithm would never work because nobody can do error correction. And so he wrote this down, and it's the first error correcting code. This is not important, but if you want to know what the states that like are the simultaneous, if you want to know what the states that are stabilized by all of these are, it looks like this. It's kind of complicated, but the point is there's 2 of them. And so we can still encode any state. Alpha 0 plus beta 1 is alpha times this whole mess plus beta times this other whole mess. That's not super important right now. I don't want you to worry about it. But the point is there are kind of 2 states out there that are going to hold our single qubit that we want to protect. Here's what I want us to think about, which is that let's say we're in a state with all stabilizers equal to 1. What happens if there's a Z1 error? And we're not going to write down states because this is going to be annoying. We're going to use rule 1. Rule 1 says that a stabilizer with an X on a qubit will flip when there's a Z error on that qubit. So my question is, what stabilizers are going to give you -1 if there's a Z1 error?
First and second.
Right. So the first stabilizer has an X on the first qubit, so it flips. The second stabilizer has an X on the first qubit, so it flips. All of the other ones have either Z's on the first qubit or nothing on the first qubit, so they're not affected by this error. So Z1 error there flips both of those stabilizers. Okay, let's just crank through these. What happens if there's an X error on the 5th qubit? Which stabilizers flip?
5 and 6.
5 and 6. Awesome. And then what about if there's a Z error on the 9th qubit?
8.
Not quite. Z error.
Sorry, 1. Yeah.
Yes. Yeah. An X error on the 9th qubit would flip qubit as stabilizer 8. This one flips stabilizer 1. The point is that I want you to get, kind of be convinced of is that we're correcting both Z and X errors. And you can go through yourself. I'm not going to go through all 18 possibilities, but you can go through yourself and convince yourself that this qubit can correct X1 errors, Z1 errors, X2 errors, Z2 errors, X3 errors, Z3 errors, all the way down the line. So it can detect both single X and single Z errors. And then, as I alluded to before, this means, I'm not going to prove it, it can detect every single qubit error in the world. Okay, so we're almost done. Just a couple more, like 2 more exercises. So let's do the reverse. Okay, so we showed that like if there was a Z9 error, then stabilizer 1 would have flipped. Now let's say you've measured that stabilizers 3 and 4 have flipped. Can you tell me what error happened?
X2.
Right, the thing that flips both of those is X2. What about only stabilizer 5 flipped?
Either X4 or X5.
Right, but what would happen if X5 happened? If X5 happened, there'd be another stabilizer that flipped. If an X5 error happened,
So only
then
X4.
6 would also have flipped. Does that make sense? So we know that X4 had to have happened. Okay, and last one, that stabilizer and that stabilizer alone flipped. What error happened?
Z7, Z8, Z9.
Right, so this one's weird, right? So if the first stabilizer flipped, it could have been Z7. Like that's the thing that flips the first stabilizer and nothing else. But it also could have been Z8, or it could have been Z9. And we can't tell the difference between those 3 things, which seems to be bad, right? If we think Z7 happened, but actually Z8 happened, that seems like we're not doing the right thing. So it seems like maybe Shor screwed up somewhere. But there's a little thing to notice that means that a Z7 error and a Z8 error are actually the same error. So remember that we're in a state where Z7 times Z8 acting on psi is just psi, right? Because we're in a state where Z7, Z8 has a value of 1. What that means is we can bring the Z8 over to the other side. What it means is that Z7 times psi is equal to, sorry, there's a question in the chat. Why can't Z1, Z2, or Z3 have happened in this case? Because Z1, Z2, and Z3 would have also flipped the second stabilizer. So if we measured that the first stabilizer was -1, but the second stabilizer was still 1, then we know that Z1, Z2, or Z3 didn't happen. So it had to have happened in this area, because if it happens in the first 3 qubits, then the second stabilizer is also checking those. It's just like how if we had an X error on the 5th qubit, it would flip these 2 stabilizers, but if it's on the 4th qubit, it would only flip this stabilizer. Okay, so then back to my final point, and this is going to be really important for the surface code as well, is that we can't tell whether a Z1 or a Z7 or a Z8 error happened, or a Z9 error. We can't tell the difference between these errors, but it also doesn't matter because a Z7 error does the exact same thing to our state as a Z8 error. So if we think a Z8 error happened, but a Z7 error did happen, we're not wrong, because a Z7 error and a Z8 error are the same error if they happen to a state with Z7 times Z8 equal to 1. And similarly, Z7 and Z9 are the same error because you can kind of do this twice. Z7 and Z8 are the same error, Z8 and Z9 are the same error. So Z7 and Z9 are the same error. And this, just for the record, this is just called a degeneracy. This is a degenerate code that multiple errors actually are the same error. And this is also going to be true of the surface code, and it's going to be super important because the surface code is hugely degenerate. Whenever you like see these stabilizers be -1, there's like so many errors. There's almost an infinite number of errors that could have made that happen, but most of them are equivalent.
I have one question. Like,
yes.
First stabilizer gives us, like, if we apply the Z7 to state psi, it's equals to Z8 to state psi because of the first stabilizers, because it will correct either Z7 or Z8 or Z9. Can
Sorry,
you say like? what I'm saying is our first stabilizers give the same result. Either we have Z7 or Z8 or Z9.
Yes.
So if we consider that result, so can we say that Z7 on any state is equals to the Z8 on that state?
Yeah, so Z7 acting on a state is equivalent to Z8 acting on the state, as long as that state was originally one of our code states. Like, it's not true for every state, obviously, but our code states, our states that we're using to store our information, have Z7 equal to Z8 on them. That's the important point.
Okay.
Because remember, we started off with saying that we're trying to, let me back up a little for a lot. So we're trying to store our state as this big mess. And it's not important what the mess is, but the important thing is that this state has, I'm going to call this state just psi. That's the state we're trying to protect. And the important thing is that this state, if you just check, you can like look at all of these messy qubits. This state has Z7 acting on psi is equal to Z8 acting on psi, because we wanted Z7 times Z8 to just be 1. So when we wrote down a state with Z7 times Z8 equals to 1, that means we've also written down a state with Z7 acting on that state equal to Z8 acting on that state. Because this says Z7, Z8 equals psi. So we know that this must be true, which means that that implies that this is true. And yes, to the answer in the chat, this is a 9-qubit code where we take 9 qubits and store 1 qubit. This seems a little inefficient. There are better things to do after this. Somebody, I think Steen, discovered a 7-qubit code that takes 7 qubits to store 1 qubit. Then it turns out that you can write down a 5-qubit code, 5 qubits to store 1 qubit, but it's a little confusing. And also, that's as good as you can get, is 5 to 1. Okay, so we're a little over time, so I just want to give a summary and a preview of next week, and then people can either stick around and ask questions or leave, depending on what they want. So what did we learn today that's important? So we learned how to describe stabilizer codes. How do you describe them? You write down their stabilizers. And we learned the 3 rules for stabilizers. So when you write down the stabilizers, they have to disagree on an even number of qubits. They're going to, X stabilizers detect Z errors, Z stabilizers detect X errors, and a single stabilizer can't detect 2 errors on it. 2 errors looks like no errors. We've also seen how one example of an error correcting code, which is the first example, Shor's 9-qubit code, can detect both single qubit X errors and single qubit Z errors. I haven't answered a few questions. One, why is it enough to just detect X and Z errors? Are these the only types of errors that can happen? Definitely not. If you're interested in this question, you can, again, read any of the notes that I posted on the Discord, but I'm just going to say that we're focused on detecting X and Z errors. And then 2, what if 2 errors happen at the same time? The repetition code that we saw can only detect a single error. It couldn't detect 2 X errors. Shor's code has the same problem. It can only detect a single error. So what if we wanted to be able to detect against like 3 errors? So what are other types of errors? Somebody asked in the chat. So we could have a Y error. We could have a small rotation about the Z axis. We could have a small rotation about the X axis. We could have an erroneous Hadamard operator. We could have an erroneous S operator. In general, we could have any unitary operator accidentally applied to a qubit. And we've only shown that we can detect an X error accidentally applied or a Z error accidentally applied. But there's a whole continuum, like basically any rotation on the block sphere could be accidentally applied. And we've only shown that we can correct a 180-degree rotation about the z-axis and a 180-degree rotation about the x-axis. So then next time, what are we doing? We're going to study the surface code. The surface code is just the stabilizer code, but it has a lot of geometric structure to it. It has a lot of qubits and a lot of stabilizers. And the nice thing about the surface code is that everything we learned today about Shor's code applies to the surface code. It's just a bunch of stabilizers that detect errors simultaneously. And what we're going to see is that the Shor's code, or that the surface code, as opposed to Shor's code, can correct lots of simultaneous errors. And if we want to make it better and better and better, we can just use more and more qubits on the surface code, and we can just make it arbitrarily good. So that's next time. This is probably the most exciting part of quantum error correction, and it's a very beautiful code. And the more you study it, the more kind of clever things you see about it. And that'll be next time. So now we can just stick around and talk and ask questions if anyone has any. So there's 2 questions in the chat. One is error correction a solved problem? It's a solved problem in the sense that we have codes. The Discord is, yeah, the community Discord. And there's a events channel where I posted some stuff about this. So is quantum error correction a solved problem? It's a solved problem in the sense that we know about codes that seem to be simple to implement, that can correct pretty high rates of errors, and that we can kind of do everything we need to do with them. Meaning that, you know, we can encode a state, and then on the encoded state, we can apply gates to the encoded state. We can read out the encoded state. This is the surface code. Surface code we know how to do basically everything for. It's not a solved problem in the sense that the surface code is still not as good as we would like it to be. The surface code requires a lot of qubits to encode a single qubit. And it's very, very hard to apply certain gates in the surface code. And what that means is that there's still a lot of active research in coming up with other kinds of error correcting codes. There are certain codes that on paper are much better than the surface code, but require you to wire your quantum computer so that very distant qubits are like connected directly by wires. And this becomes a challenge for a lot of qubit platforms. One thing that the surface code has that going for it is that you can lay out your qubits just on a plane and they're just locally connected to each other. And so that's why people like the surface code a lot. But there are other codes that have other properties that are kind of nicer than the surface code, and that they encode more logical qubits using fewer physical qubits, or there are easier ways to apply gates to them. So I guess what I would say is that we know error correction is possible. And so this isn't like a question of like, is it even possible to build a quantum computer? We know it's possible to do error correction. What's not clear is exactly what the best way to do error correction is. Right now, the surface code is the leading candidate, but that could change in the future. So then I'm just going to go down the list. Is there a code to mitigate or correct chaos in the qubit state? And then you kind of answered your own question, because yeah, any error introduced because of some sort of like fluctuations in the surrounding electric and magnetic fields, changes in the weather, you know, whatever, any sort of random chaotic error can actually be mapped to some combination of X and Z errors. Every single error in the world can be mapped to a combination of X and Z errors. And so this code detects any kind of error you want it to, it turns out, which again, I haven't proven, but it's not too bad to prove. And then somebody asked the question, can you say something about the toric code if possible? So I'll say this about the toric code. The toric code is the surface code. People use these 2 words, but they are essentially the same thing. The toric code, as the name implies, it's on a torus. So you imagine you have some like, let me find a piece of paper to roll up. Okay, so you imagine you have some piece of paper. So imagine that this was where your qubits lived. They just live on this sheet of paper. That would be the surface code. The qubits live on a sheet of paper and will, detect stabilizers on them. The toric code is exactly the same, except we've rolled the sheet of paper up and connected these edges. And then we've also rolled it up and connected those, so it looks kind of like a donut. So some of our stabilizers act on qubits over here and qubits over here. And that's why we need to roll it up, because we don't want our stabilizer to have to like go over here and over here. We want them to kind of like measure nearby qubits. So we roll up our piece of paper. There's no advantage to the toric code over the surface code. The toric code just came first before people realized that you didn't need to have this donut shape. You could put it on a piece of paper. Formally, the toric code does encode 2 qubits, whereas the surface code encodes 1 qubit. But the toric code also, it's very hard to do anything else with it. It's very hard to apply gates to the toric code. It's very hard to physically build the toric code. So it doesn't really have any advantages over the surface code. The only reason that it exists is because Alexei Kitaev first wrote down the toric code, and then later with Bravi realized that, oh, you can actually just put it on a piece of paper. You don't have to roll it up. Okay, if I'm evolving qubit 1 under some Hamiltonian, do I need to entangle qubit 1 to some qubit 2 on which I'm going to apply the stabilizer? How can I know? Sorry, I'm not sure I understand. How can I know what?
Can I ask one question?
Sure. I'm not sure I understand the question in the chat, by the way. So if you could clarify it or unmute yourself, then we can talk about it. But yeah.
No, sorry,
Yeah.
that's not mine. It's
Yeah,
a
yeah,
different.
yeah. So you can go ahead and maybe he will clarify.
Okay, so if I understand correctly, these stabilizer codes are just extra qubits which we only measure in particular basis all the time.
Right.
So is it like continuous measurement? Like how periodic do we measure it, and what is the process of measuring, or we measure all the stabilizer code at the same time, or is there some pattern?
Right. So let me tell you what the ideal is. The ideal is you measure them all simultaneously, and you measure them as fast as possible over and over and over again. And the reason is the reason you measure them over and over and over again as fast as possible is, okay, let's say we're in the repetition code. Yeah. So we just have the stabilizer Z1, Z2, and we have the stabilizer Z2, Z3. This code can detect a single error. So if a single error happens, we know about it. But if 2 errors happen, then we don't know about them, right? Because we saw, for example, that like an X1, X2 error was equal to X3 error. What that means is we need to measure these stabilizers over and over and over again. So each time we measure them, we can detect an error and then correct it. But we have to measure them fast enough so that 2 errors didn't happen between the last time we measured and this time. Like we have to correct fast enough that on average, there's only at most one error happening between the 2 measurement rounds. Because if we wait too long, if we like measure the stabilizers and we're like, nothing happened, I'll go away and come back and measure the stabilizers again. If I wait too long, then maybe like 5 errors have happened and I can't possibly correct them. I have to measure over and over and over and over and over again so that the time between measurements, there's only enough time for about 1 error to happen maximum. And so you want to measure them as fast as possible, and you want to measure them simultaneously. And the reason you need to be able to measure them simultaneously is as we get to bigger and bigger codes, there's going to be more and more stabilizers. So if you measure the first one and then measure the second one and then measure the third one and then measure the fourth one and then measure the fifth one and then measure the sixth one, you've waited too long before you go back to measure the first one, and definitely like 17 errors have happened by the time you get back to measuring the first one. So you need to measure them all simultaneously over and over and over again, so that you're not waiting longer and longer the larger you make your code. Because if you make your code larger, but then you have to wait longer to measure the stabilizers, you're kind of in trouble, because more errors are happening.
Got it. Thanks.
Okay, let me look back in the chat. Okay. I'm a condensed, oh, wait. I'm a condensed matter person. I'm studying a model related to the Torah code. Your answer makes me a bit sad. I don't think you should be sad. I think I'm saying that anything you find for the Torah code, you can also unfold it and it will still be true. It's often convenient to study the Torah code because periodic boundary conditions are nice for theoretical reasons. But things that you learn about on the Torah code, there's kind of like a two-step process. You learn some topologically ordered model in periodic boundary conditions, and you like try and figure out everything you can about it. And then there's a second step, which is, can you open the boundaries? Can you put it on a flat piece of paper? And those are both non-trivial steps, and they're both very important. My guess is that anything you find about the Torah code, there will be a way to unfold it. And so it'll be also applicable to surface codes. This is kind of a process that I had a nice front row seat to this year, where somebody discovered a new model related to a new error correcting code that was called, I mean, it doesn't quite have a name yet, but maybe it's the hexagon code, or maybe it's the Floquet code, or like people are naming it different things. But it was first discovered using periodic toric boundary conditions. And they published a great paper on it, and they just used periodic boundary conditions. And then they mentioned that, you could probably unfold it and introduce boundaries. Then somebody else wrote a paper about how they proposed to unfold it, how they proposed to like put it on a piece of paper instead of on a torus. Then it turned out that somebody else pointed out that that was wrong. In fact, they had done it incorrectly. And then there was a second paper where somebody did it correctly. So these are all non-trivial steps, and they are all like important parts of the research. The first step of like coming up with something new and clever on a torus, and then the second step of like figuring out how to take it off the torus and putting it on a piece of paper. Those are both good research problems. Okay, so then another question in the chat. How can I know the error on qubit 1 is going to be the same the next time I do the measurements? Are there codes for time-dependent errors? So these codes all work for time-dependent errors because, okay, there's an X error on qubit 1. You detect it, and then what you should do is you should correct it by applying a second, like if a certain operator happens on this qubit and you detect it, you should apply the inverse operator. The inverse of X is just X. So you just apply another X error here. So then the next time you come and measure the stabilizers, you're expecting no errors to happen. And there can be a new time-dependent error that's like a Z error on a different qubit. And then you detect it and you correct it. And then you wait a while, and then there's a new error on a different qubit, and you detect it and correct it. So all of these codes work for time-dependent errors. The kind of trick is if the probabilities of errors is changing over time, then like the optimal code might change over time. So for example, the first code we used could correct X errors, but not Z errors. So if most of the time you're seeing X errors, that's a fine code to start with. On the other hand, if at the beginning of running your algorithm, you're seeing mostly X errors, but something happens to your machine, somebody bumps it, and then all of a sudden you're seeing mostly Z errors, then that's a bad code to use. But if you use like Shor's code can detect any error. So it doesn't matter if the probabilities are slowly changing over time. As long as you're continually correcting these errors, you can always use one of these like universal codes that corrects every error. Okay, and then finally a question, X, Y, and Z, these are the Pauli matrices? Yes. So I define the X operator to be the thing that takes 0 to 1 and 1 to 0, but we can write this as a matrix. It's just 0, 1, 1, 0. And that's the Pauli matrix. And then similarly, you know, I was saying that Z acting on 0 gave you 0, and Z acting on 1 gave you -1. But this is the same as saying that Z is the matrix 1, 0, 0, -1. And then, you know, Y, you can get it by multiplying the Pauli matrices together. So this is 0 minus I 0. Other questions? Okay, great. 2 more questions. These are good. So what are the typical errors in IBM's NISQ quantum computer? Well, honestly, the biggest error in IBM's quantum computer that I've noticed is that the readout is not very good. So if you're running a short quantum circuit, you're usually dominated by errors in actually doing the Z measurement at the end. But if you're asking what the errors on the gates are, the errors on most qubits are dominantly Z errors. And what that means is that you can come up with some small, like I showed a repetition code that only corrects X errors, but you can modify it to be a repetition code that only corrects Z errors. And this is fine. Some of IBM's gates, in particular their C0 gate, has a fairly high Y error rate as well. But if you just leave a qubit alone, it'll just mostly have Z errors. And IBM had, like, if you go into IBM Quantum Experience, they have, like, you don't have to run it on their things. They have noise models for all of their quantum computers that, like, tell you approximately what the noise is in their idle things and in their gates. And you can look this up in Qiskit or whatever. Okay, so this is an interesting question. How can we differentiate an X error with an intentional X gate? So this is a very good question. So let's say we're so let's say we're in the 3-qubit repetition code. So the stabilizers are Z1, Z2, and Z2, Z3. And so the state I'm in is alpha times 0, 0, 0 plus beta times 1, 1, 1. Now, if an accidental X error happens,